This is a talk that introduces a sparse regression solution that is bias-free and has a set of guaranteed consistency results. And this is joint work with Stanley Osha and Ming Yan from UCLA, and Feng Ran, Jie Chaoxiong, and Yuan Yang from Peking University. So let me introduce the problem. The problem is to recover a sparse vector x star with n components from its noisy linear measurements. V is the measurement, which is a vector with m entries. A is a given matrix. Epsilon here is a zero mean unknown noise. Our focus is the underdetermined case, where the number of measurements is much less than the number of unknowns in X. One of the most well-known approach to recover a sparse X star is the LASSO approach, but the solution of LASSO is biased. Now, in order to avoid bias or reduce bias, Fan Li suggests that minimization should use a non-convex plier, for example, something called SCAD. So today we're going to introduce an approach that'll keep the convex plier but replace minimization by something else. So here's the outline of this talk. We're going to review LASSO and explain why its solution has bias. And then we shift our focus to a new regularization path, and this path is given by an ordinary differential inclusion. And this ordinary differential inclusion is going to use convex plier, and we're going to prove the solution is free of bias and has theoretical property. And also a certain point on the regularization path is provable we have the sign and L2 consistency. And then we start to talk about the computation of this path, either exactly or in approximate fashion. It turns out there's a very interesting way, so that you can only make a two-line change to your existing code, for example, your LASSO code, and then have approximation to this path, the new regularization path. Let's take a look at the LASSO problem. The LASSO problem minimizes L1 of the unknown plus a parameter t multiplies the normalized least squares energy, or the normalized least squares fitting error. And m is the number of measurements, that's the normalization. And since the LASSO problem is a convex problem, the LASSO solution satisfies the first order automatic condition. And because L1 is convex but non-differentiable, so we have to use a subdifferential. So P is subgradient of L1 evaluated at the LASSO solution. Therefore, LASSO solution will satisfy 0 equals the subgradient plus the gradient of the smooth least squares fitting term. LASSO tends to return a sparse solution, which is good, but it also introduces bias. Here's the one way to see the bias. Suppose S be the support of the true signal, that is, all the non-zeros in X star, the true signal, is limited to the S index set. And also suppose that LASSO luckily recovers the exact support, that the LASSO solution has the same support as the true signal. Then it turns out the LASSO solution can be written down in the following way. It's something that we call oracle estimate plus a blue term that we call bias. The oracle estimate will have expectation equal to the true signal, because the second term in the oracle estimate depends only on the noise epsilon, and the noise has zero mean. The bias term, on the other hand, depends on the penalty parameter t and the sign of the LASSO solution. So that is a term that we want to remove. Let's look at the toy example. In this example, we want to recover a scalar x star from its noisy measurements. Assume the noise is zero mean and unknown. The best estimate of the signal is b. The LASSO solution, on the other hand, is never equal to b. When this parameter t is sufficiently small, specifically less than 1 over b, the LASSO solution is always 0. When t is bigger than 1 over b, the LASSO solution is b minus 1 over t. As you can see that the bias in the LASSO solution, in this case, corresponding to the reduction to the signal magnitude. Let's look at another toy example. In this example, we have a signal that is a vector with n components. but only one of the components is non-zero, we're making one linear measurement with noise to this vector. And the linear measurement coefficients a1 through an are sorted. The LASSO solution is sparse, first of all, so LASSO does the selection job. No matter what t is, no matter what the parameter t is, all the components x2 through xn are 0. And like the example before, when t is small enough, the first component of the LASSO solution is 0. When t is above the threshold, the first component of LASSO is a reduced magnitude estimate. Here's a more realistic example. We're trying to recover a sparse vector with 256 components from 25 linear measurements. The linear measurements are corrected by zero mean Gaussian noise. So in the plot, we're plotting the true signal versus the LASSO recovery. By the way, LASSO is also called basis pursuit denoising. That's why I put BPD in there. The x-axis of the plot is the component index. The y-axis is the magnitude of the signal. The red signals are the true signal, and the blue ones are the recovery of the LASSO signal. So as you can see, LASSO successfully selects large signals, such as this. However, on all the large signals, it returns a reduced magnitude, as we have already seen in the previous two examples, like this. It does not catch the actual magnitude. It also misses several moderate and the small size signals, like this one, like this one, and like this one. Compared to the large signals, they are not really too small. So these are called false negatives. It also introduces a small number of small signals like these, and they're not part of the true signal. So these are called false positives. But by the way, we have tuned the parameter t by hand so that we see a solution that is good to us visually. So one can remove part of the bias from the LASSO solution, and this procedure is called LASSO post-debiasing. So first get the LASSO solution, then apply this procedure. There are two common approaches to remove bias. First thing is to take the support of the LASSO solution and then solve a restricted least squares problem, where the unknown x has a constraint support that equals s. Another approach is to remove the blue term in the previous few slides that corresponding to the bias term directly from the LASSO solution. Obviously, there are some issues with these post-biasing approaches. Clearly, it's extra computation, so lots of people don't do it in practice. Secondly, because these procedures are based on the LASSO solution, you cannot remove or cannot correct false positives and false negatives that are already in the LASSO solution. Also, when you move to, say, the recovery of low-rank matrices, you're going to work with continuous support. It's not a well-defined concept of discrete support as we have used in the above. Here's our proposed approach, which we call inverse scale space dynamic. The name comes from image processing. The idea is that instead of minimizing prior plus fitting error, we evolve prior and fitting error along their sub or gradients. Specifically, we get the solution path by evolving two equations from a zero initial solution. Now, in these two equations, P is a subgradient of L1 at xt, and evolve P over time. And so the time derivative of P equals the negative gradient of the fitting error. So when we start from 0, the 0 obviously have very bad fitting, but it's completely sparse. So as we evolve, we're going to reduce the fitting error, in other words, improving fitting. and then at the same time evolve the subgradient of L1, and that'll force over the time that X to have more non-zeros in it. This mathematical equation is called ordinary differential inclusion, and this ordinary differential inclusion is well defined under the following two assumptions. So PT is right continuously differentiable, and xt is right continuous. So under these two assumptions, PT will in fact be unique, and A times xt will be unique as well. So previously we have tested LASSO on a 256-dimensional problem with 25 linear measurements. So we have seen this picture before on the left. Now we run ISS to a certain time t, and now we're plotting the solution on the right. Now when you compare the two, it's very easy to notice that ISS still doesn't recover some of the very small signals like these. They're basically because of noise, and it's a smearing of noise to prevent you from telling those signal out. Now on the recovered components, it's very easy to notice that ISS has much better magnitudes. There are still some little offs, which are basically because of noise. Now it's important to look at the small signals, and there were some false positives in LASSO, like these 2 points. They disappear now from ISS. And there were also some false negatives. For example, the signal was missing, and also this fairly large signal were also missing from the LASSO solution, but now they're recovered. They come back in the ISS solution. Now, so this is what we say ISS has less bias. Actually, it's actually bias-free in the theoretical sense. The benefits is it recovers more true signals, especially those smaller ones. It also reduces the false signals, in particular those small ones. And on those larger signals that both recover, ISS has better magnitude match. So in fact, we can obtain ISS from LASSO by removing LASSO bias at its origin. Recall, LASSO solutions satisfy this optimality condition where P is the subdifferential of L1. Now if you're differentiating this equation, the both sides of it with respect to time t, on the left hand side you're going to have P dot. On the right hand side, because both t and the LASSO solution depend on t, you will end up having this blue term. Now this blue term in fact is just the LASSO's post-debiasing solution. So if you get LASSO and then get the debiased LASSO solution, why don't you just replace it by X in the first place? That'll remove the bias at the origin. That gives the ISS dynamic. So this is why ISS works better than LASSO and also better than LASSO plus post-biasing. So here's a numerical example on prostate tumor size estimation. So this is the first example from textbook Hesty, Tipshrani, and Friedman. The problem is that we're given a bunch of data with 8 clinical features. We're going to select from these 8 features some predictors and build a linear predictor for prostate tumor size. The data is divided into 67 training cases and 30 testing cases. All the parameters of the tested methods are picked up by tenfold cross-validation applied to the 67 training cases. And then once we have the linear predictors, we test them on 30 testing cases. So the table shows the coefficients of the linear predictors. Now comparing to the 4 methods, if you count the number of non-zero coefficients, you can see these squares uses 8, subtest selection uses 5, LASSO uses 7, and ISS only uses 5. So here the winners are subtest selection and ISS. What's more important is the test error, is the prediction error. So in the prediction error, LASSO and ISS does similarly well, and they're much better than the rest two. ISS is slightly better than LASSO, but again, ISS only uses 5 predictors. And overall, ISS selected fewest predictors and achieved the best test error on this example. And we didn't cherry pick this example because this is the very first example from the textbook. So let's shift our focus to theory. The theory concerns whether there exists a time t on the path, and so the point xt will have the sign consistency, which includes no false positive and no false negative properties. The theorem says if we make the following assumptions. At the moment, we only know how to do it for Gaussian noise, zero mean, and normalized columns. By the way, if we remove the normalized columns, we can just have more parameters in the result. By making these assumptions and assuming that we have the so-called irrepresentable and strong signal conditions, which are going to come in the next two slides, we will have with high probability that this particular ISS point xt has sign consistency and is an unbiased estimate to x star. So in fact, we have a window for such a time t, and there's an explicit formula for the window. The proof is based on the next two lemmas. Now, the first lemma establishes the no false positive part. Let us define the true support S. Then onto the assumptions in the previous theorem, and that AS has full column rank, and this what is called irrepresentable condition, which basically says that any column outside the true support cannot be easily linearly represented by the columns in the support. And this condition needs to hold because otherwise the xj component cannot be told apart from those components in the support from the measurements. Now, under these assumptions, we have the following result. Upon to a time t bar, upper limit on the time, we're going to always have our point with their support within the true support. In other words, there are going to be no false positive before you pass this time, which is guaranteed. The proof is based on concentration inequality and some properties that concerning the ISS update. The second lemma establishes the no false positive and the sign consistency results. So under the assumption made in the theorem, and that the measurement over the true signal part is sufficiently strong, and the smallest non-zero signal is large enough. Otherwise, you cannot tell it from noise. So this is called the minimal strength, signal strength property. Then there exists a time which can be explicitly given in our paper, and so that the signs are consistent, and we have a property that guarantees that the difference, the L infinity difference from the true signal, is less than half of the minimal non-zero signal. There are two parts in the maximization. The first part basically guarantees that the noise contribution have to be sufficiently small compared to, this should be x min. And the second part ensures sign consistency before the upper limit of the time t star, after which the false positives will enter. Now let me explain how we actually computed the ISS solution path. Now that is to compute a solution path to these two equations. Now we compute the solution path piece by piece. So it's a piece-by-piece path. It starts from t time t equals 0, and then we're going to have a sequence of discrete times. So it's an iteration. And for every iteration, we're going to compute both p and x in this interval, tk1 to tk. Now, p is piecewise linear. P is given by the previous p, and it's some term that linear in time. And this term also depends on the previous x. Now, how do we determine the new point? The new point is basically the point where further growing such a linear equation will start to violate this subdifferential condition. Right? It is possible that such a t is infinity, and then at that time we simply reach the last piece. Now, what's important is x is piecewise constant in each interval. So when you're
at the new time, when this time is not infinity, xtk is calculated as a least squares problem with constraints. And these constraints basically, by looking at pk's, which are given from the last line, and according to the values of the pk's, determine whether a component of xi can be equal or equal 0 or positive, or must be 0 or equal 0 or negative. Now, this set of condition is simply follows from that P is a subgradient of L1 at x. Now, in other words, at every breakpoint, we have to solve a constraint least squares problem. However, because PI is going to evolve, so these PIs were slightly different from the previous ones. Basically, now some new components of X now allowed to be positive or negative, or some components that were positive or negative now have to be 0. So it's a small change to the previous least squares, and then there are ways to update the solution from the previous one. So by following the method in the previous slide, it's actually very fast to compute the path for a moderately sized problems. We're going to start evolving from t equals 0 and through finitely many breakpoints. We can show that the time breakpoints are only finite. So in finite number of times, they're going to stop. At every breakpoint, we solve a constraint least squares, which, because it's similar to the previous one, it can be solved by maintaining a QR decomposition to certain matrices and update the QR. At every iteration, it's 1 or 2 updates to the QR effectively. However, the previous algorithm isn't going to be effective on very big problems because they can have too many breakpoints. Because the previous algorithm have to go through every breakpoint. So when the number of breakpoints is big, it will be slow.
So one of the very interesting way to discretize the ISS dynamic is something called Bregman iteration. So basically, we apply forward Euler iterate to the ODE while keeping P as a L1 subgradient. And then the time of discretization is this, is pk plus 1 next point equal to the previous point times step size and the right hand side. What's interesting is this turns out to be just the first order optimality condition to an optimization problem, to the following optimization problem. Okay. Now this optimization problem can be written in a different way by a change of variable. So here you're iterating pk xk and then get xk plus 1 and then implicitly gets the subgradient of L1 as pk plus 1. So you're iterating pk xk and get pk plus 1 and xk plus 1. If you do a change of variable and merge this term into that term, right? Because pk is always in a transpose, you can do the merge. Once you merge, you find out you can always solve a problem that looks just as LASSO, except this right hand side bk will keep evolving. And this is how it evolves. From any bk, the previous bk, you simply add the residual of the current solution and add it back to bk and get bk plus 1. Now this allows you to keep your existing solver and use a small delta, because this is a forward order step. Forward order have to use small delta, and then just to keep doing these adding back residual iteration. But it turns out the total time, you don't have to do many iterations. The total time is often similar to LASSO because when you use a small delta, you give emphasis to x1, to L1, and it makes the solution easier because the solution will be sparser. So what you do is you keep your LASSO solver and keep, iteratively applying it to the same type of problem with a different input. Also, what's interesting is this derivation holds for any convex prior R rather than just X, just the X1 norm.
Now, when you have very large problems, there's a even faster alternative. This is called linearized Bregman ISS. The change is to add this blue term into the ODI. The solution will be piecewise smooth, and every piece is in closed form. And as kappa increases, the solution will exponentially fast converge to the ISS solution. Now what's nice about this is you can introduce z, that is the sum of p and 1 over kappa x. And then you can reduce the two equations into just the one equation that is an ordinary differential equation of z. In fact, the map between z and p and x are 1, 1. Given z, you can uniquely recover x and p as such. This is because p is a subdifferential of L1 at x. This kind of 1-1 map exists for any convex pair. The benefit of linearized Bregman iteration is now you can explicitly evolve this ODE. You no longer have to solve any subproblem. In addition, when the sensing matrix A is huge, now suppose you can't store it in one computer and you have to store it in a distributed way. So AL is stored in the L's computer, and then you can have this parallel algorithm, which is very simple. It basically evolves this equation by using AL transport AL separately on every CPU, and then collecting a certain sum, so that such a distributed algorithm with very sum collecting is equivalent to the original order, forward order. And there's also a way when you store A row by row rather than column by column, or you can also store A into very little blocks and break A into columns and rows and have a parallel algorithm. And also, it's very interesting to compare the linearized Bregman iteration to the iterative soft thresholding algorithm, or ISTA algorithm, ISTA iteration. ISTA iteration basically starts from xk and then multiply negative times step size alpha k and the negative gradient of the fitting term. And then you apply shrinkage, which is due to L1. And if you compare the two equations, they have the exact same components. They both have A and A transpose. They both have a step size alpha k. And they both have B. Somehow you're looking at the residual, A times something minus B. There's also shrinkage, except that there are the components are put at different places. But they have different, they actually solve very different problems. Here's the interesting thing. ISTA algorithm, in the limit, as k goes to infinity, it solves the LASSO problem. And the intermediate xk is usually dense. It starts from 0, but very soon becomes dense. And then, for a long time, it gradually, from dense to sparse. However, the linearized Bregman iteration, the intermediate solution is always sparse. That's why I make it useful as a sparse regularization path. Now, if you choose to iterate k to infinity, you will actually solve the following problem. It minimizes L1 plus the L2 squared term subject to AX equals B. And this problem itself has a very interesting property. When kappa is sufficiently large, bigger than the threshold, then the solution to this problem is actually the solution to the problem as if this term didn't exist. Now, ISS also is related to orthogonal matching pursuit, which is one of the earliest algorithms for compressive sensing. So it's an iteration of the index set S. The indices in the set S will allow it to be non-zero. So we start from an empty index set and the vector x equals 0. Now, you're going to do this, use the current x, you're going to compute this residual. Look at the large component of the residual and add the corresponding index to S. And then you have, you're allowed to solve a constraint, least squares, constraining to xi equals 0 for those outside the set. You get new x. So you keep doing this. So compare OMP to ISS. Basically, OMP will gradually increase index at S, but the only difference is those in S or not outside S. However, ISS will evolve P. For those inside S, Pi will be either plus or minus 1, but for those outside S at the moment, outside the supported moment, and the PIs are not necessarily 0. The values of PI encodes the information, encodes how likely the components is allowed to be non-zero in the future. So what I have presented before can be easily generalized. Suppose you have a convex regularization model that minimizes a prior R time parameter T and fitting term F. Fan Li says if you use convex R, there will be bias in the solution. So their solution is to making R non-convex. For example, they introduce something called SCAD. So our solution is to keep the convex prior, but instead don't minimize it. You evolve the prior and the fitting using their gradient. So you're gonna decrease the fitting energy and gonna increase the prior energy. But because when prior may not be differentiable, so you're gonna use the inclusion rather than differentiation. There are a bunch of applications that are going to be very common choice of R for different problems. Notice that R can also include non-activity and box constraints, etc., and through indicator functions, because we can also take differentiation, sub-differentiation of indicator functions. At the last, I would also mention that when f is least squares, no matter what R is, you can keep your current solver for problem 1 and just simply try running the iteration of adding back the residual. You're going to soon see a approximation to ISS and see whether that'll help your case. I believe they will. And lastly, I want to mention some of the related work in optimization image processing. It's out of statistics, but lots of the scheme were already motivated from image processing. The Bregman iteration existed long before. It's about 10 years ago for imaging and for compressive sensing. Linearized Bregman on L1 was discovered about nearly 10 years ago. About 5 years ago, Tai, Candace, and Shan have this algorithm called matrix completion SVT, which is essentially a linearized Bregman iteration, except they were using nuclear norm. There are a bunch of extensions to the discrete Bregman and linearized Bregman iterations by a student called Zhang in China, a National University of Defense Technology. There has been work that generalizes discrete results, which existed first, to the continuous setting, and this is where we get our name from. It's called inverse scale space for total variation based imaging, by Martinberger and Gilbois, Osher, and Xu, and there are a bunch of improvement to that. So let me summarize this set of slides. So what we propose to do is, instead of minimizing the sum of prior plus fitting, we evolve them. The solution paths will have a bunch of properties, including the structure you're seeking for, no or less prior than compared to the solution to the minimization problem, and often it has simple and fast algorithms. The case for L1 for sparse recovery has been covered in this following paper, which is listed on the UCLA CAM report site. It's CAM 1461. Thank you very much.